So here are some digital logic circuit sample problems. So just to get started, here's the one. So it has three problems. So I'm just gonna solve a couple of problems. So first one is write down is it says implement the following expression using standard logic gates. So build the logic gates, to get this output. So there are three problems. First one is X, which is the output. A plus B complement or inversion times C. So how do you make the logic gates combination so that you get this as output? This is the output, right? And this is really simple. And so you have three inputs, right? So and first two inputs you have to add means you have to put the OR gate. This is the symbol for OR gate, right? So you have A and B, so the output here will be A plus, and then you need a complement, so you're in a NOR gate actually. It's OR plus NOT, so A plus B complement or inversion, and you have to multiply with C, so you need this to be connected with the AND gate, and this is the symbol just like D is the AND gate, and that's it. So ABC, and your very output X will be A plus B, right, times C. So that's how you build the logic circuit, right? And you can also, if it is asking the truth table, TT for this given circuit, you can build the truth table as well. Since it is a three inputs circuit, so you'll have 8 possible combinations. So possible combinations are, how do you find that? Possible combinations, right? So it's a binary circuit, so 2, and you have 3 gates, 3 inputs, so 2 to the power 3, 8 possible combinations. So you have to build the truth table based on this. So you have, and finally X as your output. If you want to build the truth, is something called truth table. So how do you, here's the trick. So you have 8 combinations, so you first start with 0 0 0 0 1 1 1 1, total of 8, and then you do 0 0 1 1 0 0 1 1, right? And then finally you do 0 1 0 1 0 1 0 1. So that's the trick to achieve all the possible combinations, okay. And then just use the properties of the logic gates to find the output. So you can now, so 0 0 0, so from, because this is your output, right? This is your output based on that. So A plus B inversion, so A plus B will 0 plus 0 gives you 0, inversion of that 1 times 0 is 0, right? And again this is 0 0 complement 1 gives you 1. 1 times 1 is 1, and 0 and 1 combination is 1, inverse of 0. 0 times 0 is 0. So 0 plus 1 is 1, complement 0. 0 times 1 is 0. So 1 and 0 combination complement is 0. 0 times 0 is 0, right? And 1 and 0 plus is 1, and complement is, inversion is 0. 0 plus 1, 0 times 1 is 0. So 1 and 1 complement, 1 and 1 gives you 1, and its inversion is 0. 0 times 0 is 0. So 1 and 1 complement is 0. 1 and 1 is 1, but inversion makes it 0. 0 times 1 is 0. So here's the interesting thing. So here you have only one high output, right, in all the, and let's see how this happens. So if the C, right, this particular C input is high, then it produces high. In all other case, actually, right, it inputs, if so in all other case where two inputs are on, then output will be on. So this is interesting one. So just making a truth table. This is called truth table. So let me show you one more thing. This Y, and so I'm gonna show you the second one. So the second one, you have to build the logic circuit A B complement C plus A complement D plus C D complement. So how do you build the logic gates based on that, right? So first let's put A B C, and see you need a complement of B, so you need a NOT gate. This is a NOT gate. So you combine with AND gate because you need the product. AND gate is D symbol. So this is ABC, ABC. So we're done with the first. So second step is A complement D. So you already have A, so A complement D. So you need one more input, which is D, right? And then how do you get the input? So you get A complement. So this means it's not connected. So you need this product with D. So you need one more inversion here. Inversion means NOT gate, and you do the NOT gate. And finally you need C and D complement product, right? C is right here and D complement. So C you get from here and D complement, and again pass it to the NOT gate. And finally remember, all these needs to be added, right? This add. So then addition, how do you do the addition? So you need OR gate. So this is the symbol for OR gate. Okay, so that should be the logic gates for this particular. So their Y output, it will be then A complement C B complement plus A complement D plus C D complement. Okay, so that's it. And you can try the third one. So the next problem says, so based on this logic gates combination, right, show the behavior of the following circuits. So what's the logic behind this combination? Output, this is the output. So first we need to check the output equation in terms of equation, and we need to build the truth table, and based on the truth table output we need to decide what's the behavior of this circuit. So remember, this symbol is for XOR gate. Okay, all right. So here you have a complement. B and C are connected to the XOR. So XOR means, remember, this is the symbol for XOR, and this is multiplication. So output will be A complement times, right, B XOR C. So what is XOR? So XOR means XOR logic is if one of the input is high, then the output would be low. That's the I'm sorry, the main logic for XOR gate. So go back to the lecture and see the main logic behind XOR gate is if all the inputs are high, all the inputs are same, then output will be low. If if the inputs are different, say one input is 0, other input is 1, then it produces high output. So that's the logic behind this. Okay, so go back and check my lecture. So this is the output, right? And let's build the truth table first. And again, it has 3 inputs. It has 2 to the power 3, 8 possible states, possible combination. And you build similar to the other problem, where A, B, C, and then you have output, right? And do the same thing, 0, 0, 0, 0, 4, 1, 1, 1, 1. So 8 possible combination. Then you do alternately 0, 0, 1, 1, 0, 0, 1, 1. and 0 1 0 1 0 1 0 1. Okay, so that's all the possible combination, right? This is just a little trick, and here's your output. So you can build this nice table. Okay, let's see what would be the output of this logic circuit. So let's start with the first one. So A and B, right? So A is A complemented, right? Output. So this will becomes 1, and B and C is Xor Gate. So B and C, if two, if two. So if both for Xor Gate, if both inputs are same, right? It will produce 0, right? So then basically 0 times 1 is 0. Okay, so what would be this? So a complement is 1 times, so this one of the input is high for XOR gate, that will produce higher input. So high plus high is high. Okay, next, so this complement of 0 is 1 times, again one of the input is high for XOR gate, that will produce high output. So high plus high, high, right? And next, so complement of 0 is 1. So but for XOR gate both inputs are on, so output will be 0. So 0 plus 1 is 0. So again the complement of 1 is 0, so whatever we get from here will be 0. So 0, so all these will be 0 easy, because the complement of 1 will be, the complement of 1, you know, will be 0, and 0 times whatever you get will be 0 here. So whatever you get will be 0. So here's the conclusion. So just look at this logic. So you can clearly see, right, if one of the input is high, this logic, right, if one of the input is high, then the output will be high, right? In all other case, it produces low in output, 0 outputs. So that's the main logic behind this, you know, and you can check various combinations. Now let's simplify some equations, you know, logic equations with and without the De Morgan's laws. So first one is really easy. So it has two problems. So first, a plus, prove that a plus ab is, you know, a. So it's really easy. It's 1 plus b, right? And if you go back and check the logic equations rules, 1 plus anything will give you 1. Okay, so that's gonna get you just 1 times 1, a times 1, and a times 1 is a. Okay, second one, a plus b, prove that a plus b is a. So you first distribute a, right, plus ab, right, and a times a is a. If you check the logic equations and logic rules, equations rules, plus, and then a b, again back to the same. So a is common factor 1 plus b, and this will give you just 1. So a times 1 is a. Okay, so proof. Okay, next is this. So again using the Boolean algebra prove this actually. So let's take the right hand side, and we will prove that this is equal to that. So right hand side is, you have a plus b and a plus c, right, and just distribute, right? So a times a plus a times c plus b times a plus b times c. So a times a is a, right, plus ac plus, so this is ba is equal to ab because they are commutative. So a common factor from here, 1 plus c plus b plus bc. So, and again this whatever you have here, right, logic, 1 plus something is just 1. This whole thing is just 1 plus bc, and that's it. So a times 1 is a plus bc, and that proves the left hand side. This is the left hand side, right? That's really easy. So one final one. So it says use De Morgan's laws or theorem to prove the following expression. So you're given some G, some logic equation. G is A plus B C prime. So that G prime, right, this, if you take the inversion or prime of this, prove that this will get you there. So first of all, G is A plus B C prime, or inversion. So now let's take the inverse of that, or complement of that. Complement or inversion of this is A plus B C prime. You have to do the whole complement, right? Now, based on the De Morgan's laws, I showed you in the diagram, you know, so to go back and check my lecture, you can break the long bar. So here, and this, the complement of the sum is product of the complement. So if you break the bar here, it's gonna be this product with B C bar. So one more time, so you break the bar here, and this will be this is the complement of the product is equal to sum of the complements. So B plus, so if you break the bar and sum, right, is C prime prime. So that's gonna be like this, right? So A prime B prime plus, so it has double complements, C prime prime, so that's just C, and that's it. That's what we're going to prove. That's it. So just we have just used De Morgan's theorem two times. One is breaking here, one is breaking here.